So we are looking at the geometric, and again, the type of random variable that we're going to look is x, where x is the number of trials until the first success. Okay, so again, our first success is defined by finding this variable. That's our success. So we can let x be the number of samples analyzed until a large particle is detected. So this type of random variable is geometric with p equals 0.01. So using the geometric distribution, which is stated here, right here, we can find that probability. So in this case, we have the probability of x being equal to 125. That would be equal to p times 1 minus p x minus 1. We have the parameters. In this case, this is 0.01 times 1 minus 0.01 to the power of 125 minus 1, and that equals 0.0029. So again, the geometric distribution is a special case of the binomial. For the binomial, we were looking at the number of trials to find this many number of successes. Now we are looking at the number of trials to find the first success. That's the main difference. Finding the first success is geometric. Finding this many successes is a binomial, daily binomial. Okay, so let's give you the opportunity to show me how well can you apply the geometric distribution. So you can work on this problem in group of 2 or 3. So this is our first big lab. Sorry. So I already told you that this follows a geometric distribution. So I'm making things easier. Oh, you're working? No, I have to be free. Please. And you're going to have 5 minutes to work on this problem. In the meantime, I'm going to pass you this document, which is a group of tables that you're going to be needing for our next topic. You don't need it right now, but I'm going to be using it. You don't have to use it, but document that I'm passing, you don't need this document to solve the math. So if you want to just put it aside and I'll explain what you need to do with it later.
Oh, you don't have to.
It's very easy to get from there. So I think I can provide the answer. I'm going to just get it all over. Okay, you don't need it for now. This is something that we're going to use later. So that probability is 0.8. And we know this follows a geometric. This is a geometric random variable with probability equals x equals x will be equal to p times 1 minus p, x minus 1. So for part A, what is the probability that the first successful alignment requires exactly 4 trials? So this is a probability of being equal to 4, because this is saying exactly 4 trials. So we have probability of x being equal to 4, and if you substitute, we know p equals 0.8. That's the probability of a success. So we have 0.8 times 1 minus 0.8 to the power of 4 minus 1. And that is 0.0064. Any questions? Okay. Part B. What is the probability that the first successful alignment requires at most 4 trials? So the key word here is at most. So when you see at most, you know that you're looking at an upper bound. So this is the probability of something being less than or equal. In this case, it's 4. And you know that probability for a discrete random variable is the summation from 0 to x. So this is x equals 0 plus the probability of x equals 1 from the probability of x equals 2 plus the probability of x equals 3 plus the probability of x being equal to 4. So if you substitute this x into the equation, you're going to have one expression for each. Okay, so you're going to have the summation for each. So for instance, you're going to have 0.08 times 1 minus 0.8 to the power of 0 plus to be x0, so this should be 4. Yeah, you don't need 0. Yes, because you need at least one trial to get a first success. That's correct. So this will be 0, this will be 0.8, 1 minus 0.8, 1, and so on, until you get to 0.08 times 1 minus 0.8 to the power of 3, and that is equal to 0.9984. And part C is basically the complement. Is what is the probability that the first successful alignment requires at least 4 trials. So we're looking at the lower bound. Lower bound is x greater than equal to 4. So, I'm sorry. To be greater or equal to 4. So this, it is, again, when you have this type of problem, the easy way to solve it is to look at the complement. So this is going to be equal to 1 minus the probability of x less than or equal to 3. And this is 1 minus the probability of no, because 4 is included. Yes, 4 is included. So it should be x equals 1 plus the probability of x equals 2 plus the probability of x equals 3. And when you solve this, this is equal to 0.008. Any questions? How many of you are able to solve it? Good. For those of you that weren't able to get the answer, is there anything in particular that is causing you problems? Okay, so again, for geometric, you want to identify random variables. That's basically looking at the number of trials to get the first success. Now we're going to transition to another distribution, which is also a very important distribution, and I will say this distribution is the most important distribution from the discrete group. Okay, so the Poisson, if you haven't seen the Poisson yet, you'll see this distribution a lot in your future courses. So it's called the Poisson distribution and also the Poisson process. So in this distribution, the number of occurrences in a given interval or region with the following properties. This distribution is memoryless memoryless, which means that anything that happens before the event that you're looking at does not affect the probability of the event that you're looking at. So the number in one interval is independent of the number in a different interval. Okay, so that probability of looking at one interval does not affect the probability of a different interval. The probability of occurrence during a very short interval or a small region is proportional to the size of the interval, as doesn't depend on the number occurring outside the region or interval. And the probability of x being greater than 1 in a very short interval is negligible. And you'll see those properties in a second. So when do you use the Poisson? For example, if you're looking at the probability of the number of bits transmitted per minute, if you're looking at the number of calls to customer service, or if you're looking to predict the number of calls to a customer service in an hour, if you're looking to predict the number of bacteria present in a given sample, the number of hurricanes per year in a given region, again, all those examples are looking at the number of occurrences in a given interval. Okay, so you're looking at an interval and you want to know what's the probability of these numbers of occurrence within that interval. So the probability associated with the number of occurrences in a given period of time is given by this expression, and this is what we call the Poisson distribution. So here we have two parameters. We have lambda and t. Lambda is the average number of outcomes per unit time or region, and t is the time interval. X is basically looking at the number of occurrences. So again, we have lambda, which is the average number of outcomes per unit time or region, and t, which is the time region that we are looking at. And the expression has an exponential to the power of lambda t, of minus lambda t, times lambda t to the power of x divided by the factorial of x. The other interesting property of the Poisson is that the mean and the variance is the same, which is lambda. So if x is a Poisson random variable with a parameter lambda, then the mean or the expected value and the variance is the same. This time defined by lambda. So let's look at this problem. So here we have an average of 2.7 service calls per minute are received at a particular maintenance center. The calls corresponds to a Poisson process. So the problem is already telling you that this follows a Poisson process. To determine personnel and equipment needs to maintain a desired level of service, the plant manager needs to be able to determine the probabilities associated with the number of service calls. So in this is a very typical problem, especially if you're in a management position. You're trying to find out what's the number of resources that you need to accomplish a specific task. In this specific example is to provide service, determine level of service. And you want to know how many people do you need to hire, or how many resources do you need available. For this type of problem, we are using the Poisson to predict the number of calls that we're going to have. And based on that, then you can decide how many people do you need to provide the service. So the problem is asking, what is the probability that fewer than 2 calls will be received in any given minute? So what will be the time units that we are looking at in this problem? It's minutes. From this setting, so we are looking at the number of calls in a minute. So right away we can identify t, which is minute, 1 minute. And what is the average number of service calls per minute received in any particular at a particular minute centers? 2.7. So we know that this is lambda equals 2.7 and this is calls per minute. So the average of 2.7 service calls per minute are received at a particular maintenance center. So we're going to use that expected value, and we're going to use the time unit to compute the probability that fewer than 2 calls will be received in any given minute. So we express our random variable as the number of calls per minute and we are looking at the probability of x being greater, equal, less than 2, correct? And since this is a discrete distribution, we know that to look at that probability, we need to compute the probability of x being equal to 0 and plus the probability of x being equal to 1. So we know the parameters already. We know this follows a Poisson. We have lambda, we have t. We can substitute those parameters into the Poisson distribution and find the probability. So this will be equal to e minus 2.7 times 2.7 to the power of 0 divided by 0 factorial plus e to the minus 2.7 times 2.7 1 factorial. And this is equal to 249, which is about 25%. So there's a 25% that we will receive less than 2 calls per minute in this call center. Now I want you to look at the tables that I provided you, this table. These are tabulated probabilities for 3 different distributions. You'll see the first page shows the binomial distribution. So if you're solving a binomial distribution problem, you can use these tabulated tables to find the probabilities without having to compute them. Okay? So the important thing to notice from, let's start with the binomial, is that you have certain parameters that are for each table. So let me show you the table here. And this is going to facilitate the computation of the probabilities a lot, at least for these 3 distributions. So okay, so we start with the binomial. Notice that we have on the first column we have the parameter n. So maybe if I take that out. So if, remember, for the binomial, you have the number of trials and the number of success, right? So we have n and r. So those are the first 2 parameters that you need to identify in order to use these tables. The other thing that you need to be aware of is it gives you the cumulative distribution. Okay? So if you find the probability of x being equal to 2, that's not the probability that this is going to give you. This is going to give you the cumulative up to 2. So it's going to give you the probability of x equals 0 plus the probability of x equals 1 plus the probability of x equals 2. If you want to find the probability of x being equal to 2, then you have to look at the difference between x equals 2 minus x equals 1. And I'm going to show you how to do that with a Poisson. I just wanted to give you an introduction, tell you that the table is also available for the binomial, and you need to be careful when you look at those probabilities because you need to be aware of the parameters for the first 2 columns. So if you're looking at the number of trials being equal to 10, then you know that you have to look at this column and find the group of tables or the group of numbers that corresponds to n equals 10. Okay? So let's look at the Poisson. So the Poisson table is on page 4. So if you go to page 4, Then you're going to find the tables for the Poisson distribution. And for the Poisson, we have R, and we have mu. So in the problem that we just solved, we're looking at lambda being equal to 2.7. So maybe this is not the best example to use because we don't have the value for 2.7. We have 2.5 and we have 3.0. So in the case that x equals 2, yeah, we don't have the value for 2.7. I apologize for that. So I guess for now, we're just going to go back to this later with a different example. But for the problem with these numbers, it's very easy to solve. It's just computing these two. But I'm going to show you how to compute it when we have a lambda that is included in the table. And I apologize for that again. Okay, so let's move to the next example. Yes, in this one we have again a similar type of environment. The number of telephone calls that arrive on the phone. The phone exchange is often modeled as a Poisson random variable. Assume that on the average there are 10 calls per hour. And you want to know what is the probability that there are exactly 5 calls in 1 hour. So again, we know that this follows a Poisson distribution. We are looking at a specific number of events happening within this time frame. So X follows a random variable of the number of calls in 1 hour. And we know that on average there are 10 calls per hour. So lambda is 10 calls an hour. And our time units is 1 hour. And the first part is asking what is the probability that exactly 5 calls in 1 hour. So how would you, is that an equality or equality? X equals 5, correct. Because it's exactly 5. Okay? So this is going to be equal to e to the minus lambda t times lambda t x divided by x factorial. So in this case, we don't have to look at the cumulative values because we are looking at an equality. So here we have e to the minus 10 times 1, 10 times 1 to the power of 5 divided by 5 factorial, and that should be equal to 0.0378, which is about 4%. And that probability is very low. So the chances of having exactly 5 calls in 1 hour is very low. Part B, what is the probability that there are 3 or fewer calls in 1 hour? So how would you state that one? That's correct. And that's why, because 3 or fewer, so we are looking at an upper bound. That's the top value, 3. And we want to know what is the probability of having 3 or fewer. So here we have less than or equal to 3. Again, we have the same parameters. This is in 1 hour. So if you were to compute this, this is the probability of x being equal to 0, plus the probability of x being equal to 1, plus the probability of x being equal to 2, plus the probability of x being equal to 3. So for that case, you need to substitute into this expression for each x. Let's go back to the table. I think we can find that probability. So if we go to, again, page 4, let's go to page 5. Now we look at lambda. Again, mu is our expected value, right? So mu is right here. What is our expected value for this problem? The expected value of a Poisson equals lambda. And we know lambda equals 10, right? So we can come here and find mu, which is equal to lambda. Our expected value is lambda. And in our case, that equals 10. Okay? So we're going to use this column. Again, this is page 5. So we found lambda. Now we're looking at x. This table, in this problem, we are looking at the cumulative up to 3. So r will be equal to 3. So on the intersection of that row in this column is our cumulative probability. So in this case, the probability of x being less than or equal to 3 is 0.0103. Okay? But again, you need to understand what mu is. Mu is lambda. So if lambda is stated as one of the options in the table, then you can use the table to find that cumulative probability. Yes?
So that gives the probability of x being less than or equal to 3, not just less than 3. Like we wouldn't have to take that and then add it to the 2 and then add it to the 1 to get less than or equal to 3?
No, this is cumulative. So this is going to give you from 0 to 3.
Okay.
Now, if you want to find the probability of x being equal to 5, like on the first part, then you're going to have to, just want to make sure, so for x equals 5, you're going to have to look at the difference of 5 minus 4. Because that's going to give you just the probability for 5. And if you do that, you should get the value that we got, 0.0378. So let me copy that here. Everybody's following? This is very important. If you get this, then it's going to save you a lot of time. Because you just can go press the probability and find it here at the table. Okay? So, for this part B, we are looking at the cumulative less than or equal to 3. So this is going to give you the cumulative. So for that case, it's this number. I'm going to give you the tables that you're going to need for the exam. So in the exam, yes, you're not going to have the whole file, but I'm going to give you snapshots of the areas that you will need. Okay? So yes, you're going to have these available in the exam. So this is cumulative. If you want to find the probability of x being equal to 5, that will be P of x being equal to 5. From the table is probability of x being less than or equal to 5 minus the probability of x less than or equal to 4. And for this problem, this is 0.0671 minus 0.0293. And that difference should be around this number. Check that for me. Is the same? Yeah. Okay? Does that make sense? So cumulative given, if you look at the equality, you have to do that process. So looking at the table, so from table, oops. So from the table, we get this is going to be equal to 0.0103, which is also a very low probability, 1%. It's about 1%. Now part C, what is the probability that exactly 15 calls in 2 hours? Okay, so this problem, this last part has an extra difficulty. Again, hours, the time it is already used to solve the first 2 parts. 1 hour, right? Now we have what is the probability that exactly 15 in 2 hours. So that changes a little bit the problem. And if you can see here, that's why we keep our t parameter into the probability. So we can see this as a different random variable. I'm going to call it y, which is the number of calls in 2 hours. So in that case, lambda t is 20, and we are looking at the probability of y being equal to 15. So in this case, this is e to the minus 20, 20, 15 divided by 15 factorial. If we go to compute this, this is 0.0516. If you go to the table, let me wait for you to write that down. Now instead of looking at mu equals 10, we have to look at mu equals 20. And we don't have that table. Yeah, we have until 18. So in that case, we're going to have to compute the probability. But again, I'm going to make sure that for the purpose of the exam, you're going to have the numbers in the table. So that probability is going to be 0.0516. Any questions? Okay, so again, this is a Poisson. We have an extra example. So I'm going to give you a minute to work on that one. And if you want to, you can work on that on your own. If you want to work on a separate page and submit it, you get it right, I'll give you a bonus point for the next exam. So here we have also a Poisson process. We have the number of content changes on our web page, website, follows the Poisson distribution with a mean of 0.25 per day. And the question is, what is the probability of 2 or more changes a day? And what is the probability of non-content changes in 5 days? And what is the probability of 2 or fewer changes in 5 days? So we give you 5 minutes, work that on your own. And again, for this particular problem, you don't have to solve it. I mean, what I mean is solve it in a calculator, but you need to express everything, like the whole expression. I mean, state the solution, but you don't have to solve it using the calculator. Yes, sir. If you can put the expression for the problem with this value, yes, okay. Yes. In addition to use the probability of x plus the probability of x plus the probability of x, also use the Poisson formula and substitute the parameters. The only thing that you don't have to do is to get the actual solution. But I want to see the whole thing, the expression. Yes, so we're including the expression, right? Let's say this is x equals 5, then you need to show me e to the minus something lambda t. Okay? And with the real values for the problem. Yes, individually. You need to submit it individually. You're done? Just give it. I'll correct them all. Oh, can you use a separate sheet? Yeah. You have 2 more minutes. Don't forget to put your name on the paper. And also remember to bring those tables to class for now. We don't leave them at home because we're going to be using them. Yes. Yeah. 1 minute. Okay, so time's up. Papers. And you can pass papers to this side of the room. Papers. Papers. What else? Okay. So let's solve the problem. So we have the number, I'm sorry. Anyone else? Papers? Have all the papers. Okay, good. So number of content changes on a web page or website follows a Poisson distribution with this mean, 0.25 per day. Okay, and the first question is, what is the probability that of 2 or more changes in a day? So again, let's call X number of web page or website content changes per day. This is per day. And we have lambda equals 0.25 per day and t equals 1 day. So A, what is the probability of 2 or more? P greater or equal to 2, which is the same as 1 minus the probability of x equals 0 plus the probability of x equals 1. So to express this as a Poisson, we have e to the minus 0.25 times 1, 0.25 times 1 to the power 0, 0 factorial, plus e to the minus 0.25 times 1, 0.25 times 1 to the power of 1 divided by 1 factorial. And that equals 0.026. You don't have to show this, but just for the purpose of having the answer is around 3%. That's the probability. B says, what is the probability of no content changes in 5 days? Okay, so you know that lambda is expressed in terms of 1 day. So we need to change the random variable to 5 days. So we're going to call y number of website content changes in 5 days. So we have the probability of y being equal to 0 is going to be equal to e to the minus 0.25 times 5, 0.25 times 5 to the power of 0 divided by 0 factorial. And that is 0.287. I was looking at some of the papers and some of you forgot to multiply times 5. Okay, so make sure that when you look at the time units, you are using the right time units. Part C is the same. What is the probability of 2 or fewer changes in 5 days? So we are using y. Probability of y being less than or equal to 2. And this is the probability of y being equal to 0 plus the probability of y being equal to 1. Y being equal to 2. And we know the probability of y being equal to 0. So this is 0.287 plus e to the minus 1.25 divided by 1 factorial plus e to the minus 1.25 square divided by 2 factorial. And that is 0.868. Any questions? So again, I wanted to show me this expression and this expression and this. I mean, you don't have to have this number, but the whole thing here. Any questions? Okay, so this concludes the material on discrete probability distribution. So we cover 5 distributions: the binomial, the hypergeometric, the negative binomial, the geometric, and the Poisson. Go back, review them. Again, I'm going to be available in my office. Make sure that you understand them. On Wednesday, we're going to start with the continuous probability distribution, which is a different type of distribution, and you need to understand this to be able to go to the next step. Okay, so remember the next exam is next Wednesday, next week, and I'll see you on Wednesday.
He was saying on the TI